They are among the biggest explosions of radio energy in the entire universe. They generate more energy than 1 billion suns. The energy in radio frequencies is so great that eventually the entire universe will be aware of this one explosion.
Breaking news from the cosmos. The James Webb Space Telescope, our eye into the universe's deepest secrets, has made a terrifying discovery. Betelgeuse, a star renowned for its luminous presence in our night sky, has shown signs of an impending supernova event in 2023. But as we grapple with the implications of such a stellar spectacle, a shocking revelation from the past emerges. The enigmatic supernova SN 1987A. Could the secrets of this past explosion hold the key to understanding Betelgeuse's fate? And what might the consequences be for our very own planet? Join us as we journey into the heart of this cosmic mystery. The James Webb Space Telescope has been at the forefront of astronomical discoveries since its launch. Its advanced instruments and unparalleled infrared capabilities have allowed it to peer into the farthest reaches of the universe, revealing secrets that have long eluded us. One of its most recent and concerning discoveries revolves around the star Betelgeuse and its supernova event in 2023. What's this startling revelation that the JWST has just uncovered? Let's find out. But before we get into the mysteries surrounding Betelgeuse, it's essential to understand the significance of another monumental event in the world of astronomy, the explosion of SN 1987A. This supernova serves as a crucial reference point, offering insights into the life cycles of massive stars and the dramatic ends they meet, helping us understand the mysterious behavior of stars like Betelgeuse. Recently, the telescope's near-infrared camera captured a detailed image of the supernova SN 1987A, revealing its intricate structure. But this supernova was first observed before that, in 1987, when astronomers witnessed one of the brightest stellar explosions in the night sky. This explosion released an immense amount of energy, producing a brilliant burst of light that was visible from Earth. This event is one of the closest supernovae observed in centuries. Since its discovery, astronomers have been closely monitoring its expanding debris to gain insights into the processes of stellar evolution. The SN 1987A supernova, resulting from the violent aftermath of a giant star's demise, is located 168,000 light-years away in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This supernova emits a wide range of electromagnetic radiation, from radio waves to gamma rays. It has been previously studied using renowned observatories such as NASA's Hubble and Spitzer Space Observatories and the Chandra X-ray Observatory. However, the introduction of the James Webb Space Telescope has provided an unprecedented view of this iconic supernova. The telescope's NIRCam captured the most detailed images of the supernova, showcasing its equatorial and outer rings, crescent shape, inner ejecta, and a unique keyhole structure. The center of the image displays dense clusters of gas and dust released by the stellar explosion. This dust is so dense that even the near-infrared light detected by the JWST can't penetrate it, resulting in the dark hole in the keyhole. Surrounding the inner keyhole is a luminous equatorial ring, which was formed by debris ejected tens of thousands of years before the supernova explosion. This ring also contains glowing hotspots that developed when the supernova's shockwave collided with the structure. The JWST's sensitivity also revealed new crescent-shaped structures believed to be part of the supernova explosion's outer layers of gas. While neutron stars typically form after a supernova explosion, the one in SN 1987A remains elusive, primarily due to its dense core. This explosion likely symbolizes the death of a blue supergiant star, one of the most massive and luminous stars in the universe. So as we've seen with SN 1987A, the universe is full of unpredictable phenomena. Now, Betelgeuse might just be the next cosmic enigma to shock us all. Are we on the brink of witnessing another stellar spectacle, one that could rival or even surpass the awe of SN 1987A? NASA astronomers are on the edge of their seats, because they've stumbled upon a revelation that has sent ripples through the scientific community. Betelgeuse, known for its consistent brightness, began to dim. This wasn't a gradual dimming that one might expect from a star nearing the end of its life. It was sudden, noticeable and concerning. Observations from JWST showed that the star's brightness had decreased significantly in a short span. But what could cause such a rapid dimming? Betelgeuse is not just any star, it's a behemoth. Its diameter is about 900 times that of our Sun, and if placed at the center of our solar system, its outer surface would extend beyond the orbit of Jupiter. Such massive stars have short lifespans, and their deaths are explosive, often resulting in supernovae. These explosive events are not only mesmerizing but also crucial for the universe. They scatter elements like carbon, nitrogen and oxygen, which are essential for life as we know it. In essence, the death of stars like Betelgeuse contributes to the birth of life elsewhere. Is it possible that a massive star like Betelgeuse could simply fade away without a dramatic exit? The answer is both intriguing and complex. Several theories were proposed to explain this phenomenon. One popular theory suggested the presence of dust clouds in front of the star, obscuring its light and causing the dimming effect. As stars like Betelgeuse age, they often shed their outer layers, releasing vast amounts of dust and gas into space. This material can form dense clouds that can, at times, block the star's light, leading to perceived dimming from our vantage point. In fact, recent observations have shown that Betelgeuse has been releasing an increased amount of material, leading to the formation of such dust clouds. This process is a natural part of a star's life cycle, especially for red supergiants like Betelgeuse. Another theory pointed to stellar pulsations. Massive stars like Betelgeuse often undergo periods of expansion and contraction. These pulsations can lead to variations in brightness, with the star dimming during contraction phases. This is not uncommon for stars of Betelgeuse's type. The star's immense gravity pulls its outer layers inward, causing it to contract, and then the heat from the core pushes them outward, causing it to expand. This rhythmic pulsation can lead to noticeable changes in brightness over short periods. But the most alarming theory, and one that has gained significant traction, is that this dimming could be a precursor to an impending supernova. Could we be on the brink of witnessing one of the most spectacular events in our cosmic neighborhood? The life cycle of a star is determined by its mass, and Betelgeuse, being 20 times the mass of our Sun, has always been destined to end its life in a supernova explosion. The sudden dimming could be an indication that the star is running out of fuel and is about to collapse under its own gravity. Historically, stars that have undergone sudden dimming events have at times exploded in spectacular supernovae. These explosions are not only visually stunning, but also play a crucial role in the universe's evolution, dispersing essential elements into space. The JWST began its observations of Betelgeuse long before the supernova event. Using its suite of advanced instruments, including the near-infrared camera, the mid-infrared instrument, and the near-infrared spectrograph, the JWST collected a plethora of data on Betelgeuse. These instruments allowed the telescope to capture high-resolution images, analyze the star's light spectrum, and detect minute changes in its brightness and temperature. But with all this advanced technology, how did JWST actually see the changes in Betelgeuse leading up to the supernova? The type of data JWST collected about Betelgeuse is truly astounding. For instance, the MIRI, with its ability to observe in the mid-infrared spectrum, could detect the heat emitted by the dust around Betelgeuse. This dust, a result of the star shedding its outer layers, can tell us a lot about the star's health and its imminent demise. By analyzing this dust and the light emitted from Betelgeuse, astronomers could piece together the star's recent history, its current state, and predict its future. Betelgeuse's enigmatic nature has always been a subject of fascination. Its sheer size and luminosity make it stand out, but it's the mysteries that surround this celestial body that truly captivate the imagination. For starters, Betelgeuse is a variable star. This means its brightness doesn't remain constant, but fluctuates over time. While many stars exhibit this behavior, Betelgeuse's variations are particularly pronounced. These fluctuations have been observed for over a century, and while they were initially thought to be regular, recent observations have shown them to be more erratic. This unpredictability adds another layer of intrigue to an already enigmatic star. But what causes these fluctuations? Well, this red supergiant is a bubbling cauldron of nuclear reactions. Deep within its core, hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. This energy pushes outward, causing the outer layers of the star to expand. But as they expand, they cool down, leading to a decrease in brightness. Over time, the outer layers contract again, heating up and increasing the star's luminosity. This cycle of expansion and contraction gives rise to the brightness variations we observe. So every time Betelgeuse pulsates, it provides astronomers with a window into its internal workings. By studying these pulsations, scientists can glean insights into the star's structure, composition, and even its future. For example, have you ever wondered about the colors of the stars? Why are some stars blue, others yellow, and some, like Betelgeuse, a brilliant shade of red? The color of a star is directly related to its temperature. Blue stars are the hottest, with temperatures reaching up to 30,000 degrees Celsius, while red stars are cooler, with temperatures around 3,500 degrees Celsius. Betelgeuse, with its reddish hue, is a relatively cool star. But don't be fooled by the term cool. If you were to approach Betelgeuse, you'd be incinerated long before you got close. Another fascinating aspect of Betelgeuse is its age. While it might seem like a paradox, massive stars like Betelgeuse have shorter lifespans than smaller ones. This is because they burn through their nuclear fuel at a much faster rate. Betelgeuse is nearing the end of its life, and when it dies, it will do so in a blaze of glory, exploding as a supernova. This explosion will be so bright that it will be visible in the daytime and will outshine every other star in the night sky. But the question on everyone's mind is, when will this happen? Predicting the exact moment a star will go supernova is challenging. However, the recent dimming event has led many to speculate that Betelgeuse's end might be nearer than we think. Could we be witnessing the final days of this stellar giant? One of the primary reasons for the belief that Betelgeuse might go supernova is its age and stage in the stellar life cycle. As mentioned earlier, massive stars like Betelgeuse have shorter lifespans than smaller stars. They burn through their nuclear fuel at an accelerated rate. Betelgeuse has already exhausted the hydrogen in its core and has moved on to burning heavier elements. Each successive phase of fusion produces less energy and lasts for a shorter duration. As the star fuses heavier and heavier elements, it creates an onion-like structure with different layers burning different elements. Once a massive star starts fusing iron in its core, it's a ticking time bomb. Iron fusion doesn't produce energy, instead it consumes it. This leads to a rapid collapse of the core, followed by a rebounding shock wave that results in a supernova explosion. Another reason is the observation of the star's pronounced dimming. While dimming can be attributed to several factors, such as dust clouds or stellar pulsations, the rapid and significant decrease in brightness could also be indicative of a star nearing the end of its life. Before a star goes supernova, it might undergo a phase where it ejects a significant portion of its outer layers, leading to such dimming events. So what would happen if this supergiant were to explode? The explosion of a star as massive and as relatively close to Earth as Betelgeuse would undoubtedly be one of the most significant astronomical events of our time. While the sheer spectacle of such an explosion would be awe-inspiring, the consequences of a Betelgeuse supernova would ripple across various domains, from the immediate effects in space to the long-term implications for our understanding of the universe. To begin with, let's visualize the immediate aftermath of the explosion. Betelgeuse going supernova would produce an intense burst of light, outshining every star in the night sky. For weeks, possibly even months, this once familiar star would become a beacon in the heavens, visible even during the day. Night skies would be transformed, with Betelgeuse's brilliance rivaling that of the full moon. This radiant display would not only captivate casual observers, but would also provide a unique observational opportunity for astronomers worldwide. However, the light show is just the tip of the iceberg. The energy released during the supernova would be equivalent to the energy our Sun would emit over its entire 10 billion year lifetime. This explosion would send a shock wave hurtling through space, pushing and compressing the interstellar medium in its path. As this shock wave travels, it would heat up the surrounding gas, creating a luminescent bubble of ionized material. This supernova remnant would continue to glow for thousands of years, serving as a lasting testament to Betelgeuse's explosive demise. Beyond the immediate vicinity of the explosion, the supernova would spew out a torrent of cosmic rays, high-energy particles that travel near the speed of light. These particles, primarily protons and atomic nuclei, would spread out in all directions, some of them eventually reaching our solar system. While Earth's magnetic field and atmosphere would shield us from the direct impact of these particles, they could influence the solar wind, a stream of charged particles emitted by the Sun. This interaction could lead to enhanced auroras, the mesmerizing light displays seen near the poles, making them visible at lower latitudes than usual. The explosion would also release a vast amount of gamma radiation, the most energetic form of electromagnetic radiation. Gamma rays, due to their high energy, can interact with other particles and produce pairs of electrons and positrons. While the bulk of this radiation would be absorbed by the interstellar medium, some of it might reach our solar system. However, given Betelgeuse's distance from Earth, this radiation would not pose a direct threat to our planet. Instead, it would add to the background gamma radiation that our satellites and space telescopes detect, providing valuable data for astrophysicists studying high-energy processes in the universe. On a more profound level, the materials ejected during the supernova would enrich the interstellar medium with heavy elements. Stars like Betelgeuse are cosmic forges, where elements heavier than hydrogen and helium are synthesized. When such a star explodes, it disperses these elements into space. Elements like carbon, oxygen, nitrogen, and even metals like gold and platinum are spread out, seeding the cosmos with the raw materials for future stars, planets, and possibly life. In a poetic sense, we owe our existence to the death of stars. The carbon in our cells, the oxygen we breathe, and the iron in our blood, all were forged in the heart of stars that exploded long before our solar system was born. Furthermore, the remnants of the explosion would offer a treasure trove of information about the life cycle of massive stars. By studying the layers of material ejected during the supernova, astronomers could piece together the star's history, understanding the processes that occurred in its core during its final days. This would provide invaluable insights into stellar evolution, nuclear synthesis, and the dynamics of supernova explosions. Thanks for watching this episode of Beyond Discovery. Don't miss the video you see on your screen, you won't believe it.